Moving on to 7-2, it's the increase in entropy principle. But one thing I did want to mention, I actually wanted to go back to this internally reversible isothermal heat transfer. So sources and sinks, they are isothermal, right? They can give off heat transfer without changing their temperature. So that a lot of times when we're dealing with sources and sinks, if it's internally reversible, or a Carnot device, heat pump or something like that, then we can just use Q over T because it's internally reversible, because it's isothermal. Another thing you probably could have guessed, this temperature needs to be absolute temperature. Absolute temperature needs to be in Kelvin if we're in SI units, Rankine if we're in English units. Okay, so let's go to the increase in entropy principle. So let's say we are operating under a cycle, so we're going from state 1 to 2, but then back to state 1. Let's say we take one path to state 2, and let's say this was an irreversible path, but then we come back a different way. Maybe we actually come back the reversible path. We know that the cyclic integral of delta Q over T is always negative or 0. So let's break this up into, if we go from 1 to 2 and then back from 2 to 1. Let's say we go from 1 to 2 just some weird way, any way that we want to, but then we come back from 2 to 1 in a reversible way. All right, so we know that the integral over the whole cycle, so if we integrate from 1 to 2 and from 2 to 1, then that's over the whole cycle. We know that this is always less than or equal to 0, right? So, but this reversible path, this reversible integral, we just defined, is the change in entropy. All right, so we're going from 2 to 1, or from 1 to 2. So we need S1 minus S2 right here. Right, that's the change in entropy if we're starting at 2 and going back to 1. So that term is S1 minus S2. This other term will keep the integral from 1 to 2 of delta Q over temperature, plus this S1 minus S2 is less than or equal to 0, right? So now I'm going to subtract this to the other side of the equation. So subtract that, put a negative on that. Instead of putting a negative on that, I'm going to switch and say S2 minus S1, and we've got this less than or equal to or greater than, depending on what direction you're looking at it. The integral from 1 to 2 of delta Q over T is always less than or equal to S2 minus S1. I'm just going to rewrite this, swap these directions. So we've got a new equation that the change in entropy, the S2 minus S1, the entropy at state 2 minus the entropy at state 1 is greater than or equal to the integral from 1 to 2 of delta Q over T. Let's write this in words. The change in entropy is always greater than or equal to, all right, and so this integral is the entropy transfer with heat. So this is the change in heat transfer, delta Q over T, the entropy that is transferred due to heat, or the entropy that is transferred as the heat is transferred. All right, so if this change in entropy is always greater than this, then let's write this a different way. The change in entropy is equal, all right, so we have this equal sign. Let's say that it's equal to this value, integral from 1 to 2 of delta Q over T plus some positive term. Right? Does that make sense? If the entropy change is always greater than some value, then let's say it's equal to some value plus some positive term. So that's just lowercase delta Q over T. Let's write this in words. The entropy change is equal to the entropy change due to heat transfer plus we'll call this S-gen, we'll call this entropy generation, entropy creation, the entropy created, or entropy generation, and this is due to irreversibilities. Due to irreversibilities. And this S-gen term is always positive, right? Because this is always greater than or equal to this. It's always positive or 0. All right, so S-gen is 0 if it is reversible. Right? Doesn't that make sense? That if this process is reversible, that is 0. Our change in entropy is just the integral of delta Q over T. S-gen is positive if it is irreversible. And is S-gen ever 0? No, this is impossible. The entropy generation term is never negative. Sorry, S-gen is never negative. Okay, so for an isolated system is also adiabatic. Right? If something is isolated, there's no heat transfer, it's adiabatic. Then there is no, this term is 0. And so for an isolated system, S2 minus S1 is S-gen. We already knew that the change in entropy of an isolated system like the universe is always increasing, always positive. And we can consider a system plus its surroundings as an isolated system. All right, if we're just looking at the system, then there might be some heat transfer, work transfer, there might be something crossing the boundaries, but if we consider the system and its surroundings, then we can say, well, that's a completely isolated system. So we can consider a system plus its surroundings as an isolated system. So For an isolated system, the entropy generation is equal to the change in entropy. So we can say the change in entropy of the system plus the change, the change in entropy of the surroundings is equal to Sgen, because for an isolated system, for a system where we're looking at the system and the surroundings, there's no Q, so there's no heat transfer, there's no entropy due to heat transfer, there's only entropy change due to entropy generation. All right, some notes on this increase in entropy principles. Processes must occur in the direction of increasing entropy in the direction of Sgen is positive or 0. Processes must occur in the direction of Sgen is greater than or equal to 0. There is no conservation of entropy. Entropy is not conserved. Right? Entropy is always increasing. So we can't keep track of the entropy. Initially, the entropy, final, the entropy entering, exiting. We're not going to do that. There's no conservation of entropy. Entropy is always conserved. And so we talked about this. This Sgen term is a quantitative. It's a quantitative measure of the irreversibilities in the process. That Sgen term is a measure of irreversibilities, and we can get a number for that now. We can calculate Sgen, and that is a quantitative measure of how irreversible it is, or maybe how close to being reversible, how close to being a Carnot, how close to being our ideal it is. That's what we can use that Sgen term for. All right, so let's look at some problems that deal with the increase in entropy. All right, so we've got a heat source at 800 Kelvin. It loses 2,000 kilojoules of heat to a sink at a 500 Kelvin. And let's compare it to B, a sink at 750. All right, so we've got some 800 Kelvin source, and it is losing Q, losing 2,000 kilojoules of heat to part A 500 Kelvin sink. So here's our source, here's our sink, and we're going to compare that to 800 Kelvin source, which is losing Q, transferring heat, same Q, 2,000 kilojoules, to a 750 Kelvin sink. So determine which process is more reversible. All right, so part A. We can calculate the Sgen. Sgen is a measure of irreversibilities. So the larger the Sgen, then the more irreversibility it is. And you can probably guess which one of these is more reversible, but we're going to calculate it. The Sgen total would be the delta S of the source plus the delta S of the sink. Okay, and do you see that these delta S's, these are Q over T, because it's isothermal, because we're assuming that the source is so large that it stays at 800 Kelvin even after it loses some of this Q. So this is this is an isothermal heat transfer process. So these are both Q's over T's. So S gen total for the first scenario, part A. The Q of the source, remember it's losing Q, would be negative 2,000 kilojoules over, its temperature, is 800 Kelvin. And then the delta S of the sink, the Q over T for the sink, it is gaining 2,000 kilojoules over 500 Kelvin. So this is, what value? Negative 2.5 plus 4 equals 1.5 kilojoules per Kelvin is the S gen of the first scenario. A source at 800, a sink at 500. All right, the second scenario, S gen total would be delta S of the source, delta S of the sink. All right, so for the source, it's still losing negative 2,000 kilojoules per 800 Kelvin. The sink is gaining 2,000 kilojoules, but now it is at 750 Kelvin. All right, what about these numbers? Negative 2.5, and this is 2.7. This turns out to be just 0.2 kilojoules per Kelvin. So which one is more reversible? Which one is more reversible? This one right here. B is more reversible. All right, and so we calculated that quantitatively by comparing the S gens. S gen is a measure of irreversibilities. So part A was larger; it had more irreversibilities than part B. Now we probably already knew this because we knew that an isothermal heat transfer is reversible. So if we could have heat transfer from 800 Kelvin source to an 800 Kelvin sink, then that would be irreversible. That's the whole Carnot principle, is to try to make that heat transfer as the temperature change as small as possible. So we probably already knew that, but now we calculated this by calculating the S entropy generation. Okay. All right, another problem with the increase in entropy principle. All right, so let's say we've got a completely reversible heat pump. Okay, we've got a Carnot heat pump. It produces heat at a rate of 300 kilowatts to warm a house maintained at 24 degrees Celsius. The exterior air, which is at 7 degrees Celsius, serves as the source. Calculate the rate of entropy change of the two reservoirs and determine if this heat pump satisfies the second law according to the increase in entropy principle. Okay. All right, so let's kind of identify what are we given? What are we given? What this 300 kilowatts that a heat pump produces to warm the house, that's the QH. That's the QH. It's a Q dot because it's power, kilowatt. It warms the house, and the house is maintained at 24 degrees C. That's the TH. And the outside cold air at 7 degrees C, that's the TC. All right, calculate the rate of entropy change of the two reservoirs. All right, so let's calculate the rate of entropy change of the two reservoirs. The delta S. Do you see that this is, assuming this is a large source and a large sink, and this is a Carnot heat pump, the delta S dot, because it's a rate, is Q over T. So the delta S, the rate of entropy change of the hot reservoir, the house, would be QH dot over TH. Okay? Delta S is Q over T if we're talking about rates. Delta S dot is Q dot over T. So we're talking about the house. And the outside air, its delta S dot would be QL from the lower, so this is really like TL, TH, and TL. QL over TL, Q dot L over T dot L. All right, so it asks us to find the rate of entropy change of the two reservoirs. So we need to find the delta S dot of the house and delta S dot of the outside air. So we actually know QH and TH. So we can real quickly go ahead and find the delta S dot of the house. The QH is 300 kilowatts. So that is the Q. Now we're thinking about the house. The house is receiving that Q. That's a Q into the house. So positive 300 kilowatts over the temperature of the house, 24 degrees C, but it's got to be absolute temperature. So this would be positive 1.01 kilowatts per Kelvin. That would be the rate of entropy change of the house. All right. To find the rate of entropy change of the outside air, we need to find this QL. We need to find this QL. So we're going to do that digging back into what we learned from chapter 6. Let's see. We could do, we've got a number of equations. We know that the work is QH minus QL, but we don't have the work, actually. We know that the coefficient of performance of the heat pump is QH over work. So let's see. What do we know? We know QH, but we don't know work. We're trying to find QL. We know QH, but we still don't know work. We're trying to find that. But you know what? Coefficient of performance is also 1 over 1 minus QL over QH. We don't know QL. I think I'm going a roundabout way to get this, because we know that this was a Carnot heat pump. We know that this was a Carnot heat pump, and so we know that the for a Carnot heat pump, the coefficient of performance is 1 minus TL over TH also. Now, I think I could have just used the ratio of temperatures to find the ratio of Q's. Going way around the bush to get this, but let's follow along with this. All right, so the coefficient of performance of the heat pump is 1 over 1 minus TL. So the TL would be 7 plus 273 over the TH would be 24 plus 273. All right, so our coefficient of performance is 17.47. And I'm going to bring that up here and say that coefficient of performance is equal to QH over W net. And I know that QH is 300 kilowatts. Let me rewrite this right here. 17.47 is 300 kilowatts over work net in. So then I know that work net in is 17.17 kilowatts. And then I'm going to plug that in way up there and say 17.17 kilowatts is 300 kilowatts minus Q dot L. So from here, I would get Q dot L is equal to 282.8 kilowatts. All right, so the question asks for the rate of entropy change of the sources. So now we're looking at the rate of entropy change of the outside air is QL over TL. And now this Q, this heat transfer, we're extracting it from the outside air, so it is leaving the outside air. So that is negative 282.8 kilowatts over 280 Kelvin. That would be the 7 plus 273. And this is negative 1.01 kilowatts per Kelvin. So I've found both the rate of entropy change of the source, rate of entropy change of the sink. And then it asks, does it satisfy the second law? Does it satisfy the second law? Well, the SGen, the delta S of the, of the whole system, of the H plus delta S of the outside air, it's got to be positive or equal to 0. And so we can see, we found that the SGen of the house was positive 1.01 kilowatts per Kelvin. The SGen of the air is negative 1.01 kilowatts per Kelvin. And so this does equal 0, which is what it should have done if it is a reversible process. And so this was a reversible heat pump. So it is true, and we calculated it correctly, that the entropy change of the house plus entropy change of the outside air should have, and it does, add up to 0. Okay, so I got one more increase in entropy principle problems. Okay, during an isothermal heat rejection process of a Carnot cycle, the working fluid experiences an entropy change of 0.7 BTUs per Rankine. If the temperature of the heat sink is 95 degrees Fahrenheit, determine the A, amount of heat transfer, B, entropy change of the sink, and C, total entropy change for this process. So the entropy change for an isothermal process is Q over T. So the amount of heat transfer, Q, is what we're looking for. Well, we knew that the entropy change was negative 0.7 for the working fluid is negative 0.7 BTU per Rankine. And so this is Q over the temperature. This is a Carnot cycle. So we know that for the Carnot cycle, the temperature of the working fluid is the same as the temperature of the heat sink. So this temperature of the working fluid, this is what we're looking at, working fluid right now, is still this temperature 95 degrees Fahrenheit, but I need to add 460 to get it to Rankine. All right, Q is negative 388.5 BTU. That is the Q of the working fluid. So the working fluid rejects heat into a sink, and so the working fluid, gives off this Q right there to the sink. All right, now let's find the entropy change of the sink. So delta S is Q over T, but now we're looking at the sink. So looking at the sink, we're trying to find the entropy change. The Q that the working fluid gives off is the Q that enters the sink, 388.5 BTU, but now it is positive. Temperature of the sink, same. And so this is the same. It's the same equation, but now it's positive. The change in entropy of the sink is positive 0.7 BTUs per Rankine, and the total entropy change for this process, total entropy change, delta S of the working fluid plus the delta S of the sink, negative 0.7 BTU per Rankine plus positive 0.7 BTU per Rankine. We already actually knew that this should be 0 because it is a reversible process, right? It's a Carnot heat rejection process, and Carnot cycles are reversible, and so for a reversible process, the S-gen should be equal to 0.